Hello everyone, this is video 3.5 looking at addition and subtraction of positives and negatives. This is probably toward the upper end of the grade level for this class, so this is probably going to be not as much in the K1, 2 domain that we've been most actively working at up to this point. This is going to be a little bit older students for the most part, but still very much appropriate for what we need to be covering for this class. So let's get started. So we need to define two terms. We have our addition identity, which is the value which, when added, preserves value. And so what we mean by that is if we were to add anything to 0, so if we do 4 plus 0, we get 4. If we do 7 plus 0, we get 7. This 0 preserves value. Whatever we add to it, it stays the same thing. So generally, we could write a plus 0 is just going to remain a. It just stays a. And so this is what we mean by identity. Now, we have to specify this the addition identity because later on we'll get to the multiplication identity. And you should know that we multiply by 0, you don't keep the same value. So there's a different identity for multiplication. So that's why we need to specify which one we're dealing with. We also have this thing called an inverse. And that is what's going to get us back to the identity. So what value do I need to add to get back to 0? So if I add 4 to negative 4, then I get to my identity. And so which one is the inverse? Well, it depends on which one we're talking about. Negative 4 would be the inverse to 4, but also 4 would be the inverse to negative 4. There's a connection between these two values and this idea with absolute value. So the two values that have the same absolute value will be inverses to each other. So if you go back and look at how we talked about and defined absolute value, this hopefully connection makes some degree of sense. We could do this again with, say, 7 or negative 7, just to mix it up, plus 7 equals 0. So again, these are going to be inverses to each other, and then this gets us back to this identity. Okay. Generally, we would write this as a plus negative a equals 0. And now keep in mind, this is going a little bit ahead, but if this a were, say, negative 7, like in this case, if a is negative 7, then negative a would be positive 7. It would be the negative of negative 7. So this doesn't mean that it has to be positive plus negative. It just means that this is a, this is the negative of a. So there's some flexibility in this. So we're going to need these ideas of identities and inverses for what we're going to be talking about today. It's going to be a pretty important part, a pretty key idea to how we're going to talk about adding and subtracting with positives and negatives. So make sure you know these two terms. It doesn't help they both start with I. That makes it a little confusing. And it doesn't help that they both kind of get used for the same thing, the same idea rather. And you need the identity, or you need the inverse to get to the identity, but you don't necessarily need the identity to get to the inverse. So they're very interwoven. It's very easy to get them confused. So it may take you some time to kind of sort them out in your head, but the more we work with it, the more we talk about it, the more it should make sense. We're going to be using two-color chips or counters or markers, depending on who you ask. They may call them different things, but the idea is still the same. And I put a link online to where there's some online two-color chips that you can use. So if you've used these before, you're probably familiar with them. If you haven't used them before, then I really recommend that you go online and do some of the problems on the homework using these so you get some familiarity with what these look like. But effectively, they are two chips, and the ones that we use in class a lot of times are red and yellow. Now, these may be really hard to see, so for the most part, what I'm going to use is I'm going to use one with a plus and one with a minus. And so it's kind of weird because we're talking about two color chips. And I'm just going to draw them in one color. But This way we'll be able to see kind of what's going on. When you do the two color chips, you have to make sure that you let students know which one is the negative and which one is the positive. So when we're doing these, the reason there are two colors is they're going to represent the two parities. They're going to represent, or the two signs, positive and negative. So we want to make sure that we make clear which one. So usually I'll write on the board, red equals negative, and then yellow equals positive, or I'll put it on the worksheet or whatever. But we want to make sure that we're really clear which one is which sign. We don't want students to do the correct math, but then get confused about the color. That's kind of not what we're here to learn. So we're going to use these to represent numbers and to represent different values. So a good starting point for this is going to be to ask students to do things like, to start, model +5. And so students are going to start 1, 2, 3, 4, 5. So not too dissimilar from using base 10 blocks. We're just using a set model. There's no place value chips for these. There's not a chip that represents +10. You can extend this into base 10 blocks, and I've seen base 10 block sets that come in two different colors. So you can do positives and negatives with base 10 blocks as well. But in my mind, once we've gotten to this point, we've already gotten to a point of abstraction to where if I need to use different place values, I could just use the place value mat. I don't need those proportional pieces quite so much, but they do exist if you want to. Anyway, so here's my +5, and then it's really important that we establish that this is not the only way to make a +5. I could also make it like this. And so we have to introduce this 0. The 0, which is my identity. And I refer to this in class as a 0 pair because it's a pair of chips that add 0 to it. So I've got 5 and this 0, which I know has the value of 5. I know adding that 0 is an identity. It doesn't change the value. And so this is still 5. And this is still 5. And this is still 5. And this is still 5. So before I get into the addition and subtraction, I really need students to understand that this 5 can be modeled a bunch of different ways. A bunch of different ways. And I could do the same thing with -5. I could put 5 negative chips and then add some zeros onto that. No matter what number it is, this is not a characteristic that's unique to 5. No matter what number it is, I can add a bunch of zeros. I can keep adding the identity to it, and it doesn't change the value. This is going to be, like I said, crucial idea before we get into addition and subtraction. So we want to go through modeling addition and subtraction with positive negatives. I'm going to break each operation into the signs being the same and the signs being different because they operate a little bit differently. So we'll go through all 4 of those cases, and then effectively we'll be done. We also need to make some distinctions in subtraction about the order of the numbers if the minuend is smaller or if the subtrahend is smaller. So we'll make those distinctions as we go. But the most basic case, 5 plus 3, is we're adding 2 positive numbers. These have the same sign, and we've already kind of introduced this idea using base 10 blocks. But now we can do the same thing with positive and negatives. We can use the 2 color chips. So 5 positives, 3 positives. I mean, the models look identical because they're representing effectively the same idea. This is addition, so we combine these into one set. I count how many I have. I have 8. Same as it ever was. It's the same story from before, so it's not that much different. Now, when we extend this into negatives, -5 plus -3, the idea is still the same. I want to take 5 negatives and then 3 negatives, and I'm going to combine them into one set. And so when I combine all these together, I have 8 negatives. And that's it. I don't need to do anything funny with the signs. I don't need to make this into -5 minus +3. I don't need to change anything around. All I need to do is recognize that I got 5 negatives and I got 3 negatives. I'm going to combine them together. And what do I have? I have 8 negatives. That's it. That's the whole story. So if I understand what addition means as the combination of sets, this problem solves pretty directly. Now let's get into positives and negatives addition where the signs are different. So if we take 5 plus -3. So I'm going to model this problem the same way, 5 positives and then 3 negatives. And so we want students to identify these pairs right here. So these are my 0 pairs. So all of these I know equal 0. They effectively cancel, right? So they're going to go away. And so I look at what's left, and my answer is going to be a +2. That's it. But before we get to this point, it's important that students are able to identify what's happening here with this cancellation, that they're able to see that really what we have here, we've changed this problem from 5 plus -3 to really 2 plus 3 plus -3, because these are inverses. And they will create this identity of 2 plus 0 makes 0. So we've really done some associativity and commutativity within this. It's very implicit. You don't necessarily need to write it out. And I mean, you can weigh the merits of showing this much detail to your students. But even if they don't see it, you should be able to recognize that's what's happening here. That we've taken this 5 and we've broken it into the part that's going to cancel and the part that's going to be left over. After this all cancels, then I can find my solution. The same thing is going to happen if I make it 5 plus 3, or -5 plus 3 rather. So -5, and then +3. And so it's the same idea. I'm going to break this 5 into 3 negatives and 2 negatives, and then all of these are inverses. So this is my -3 and +3 make 0. And so what's left over here is my -2. There's 2 negatives left over after all the cancellation. It's important that students also recognize that in problems like this, you should never have positives and negatives left over at the end of your work. If you have positives and negatives, that means there's more cancellation that can be done. So at the end, only one team should win, quote unquote. That's how it was kind of described when I first learned this. That effectively there were 2 teams, the positives and the negatives, and who wins by how much. And so in this case, the positives score 5, the negatives score 3, and so the positives won by 2. It's a cute enough model, but it is important to recognize that only one of these should be left, and if there's both of them, then there's more cancellation. Okay, so now for subtractions of positive and negatives, I'm going to break this into 4 cases here. So let's start with 5 minus 3. And as a quick refresher about what this looks like and what this means. So I've got 1, 2, 3, 4, 5. And hopefully by this point, everybody knows not to make the set of 3 as a separate set. That what we're going to do for 5 minus 3 is we're going to take my set of 5, and then I'm going to remove my set of 3, and then look to see what's left, and what's left is this subset of 2. So a set addition is combining sets together. Set subtraction is removing a subset from a larger set. So this is the distinction between the models for addition and subtraction. So if we could do this the same thing, -5 minus -3, well, the model stays the same. So we've got 1, 2, 3, 4, 5. This is my set of negative 5. And this is my negative 3 that I'm removing. And so what's left? Well, negative 2. Now, this is a really important distinction. Notice I haven't said anything about changing this into plus positive 3. There is no need at all to change the signs on anything. And yet, for most students, this is how they were sort of taught what was going on. But it doesn't make any sense because it complicates, in a lot of ways, this model. You've changed it from all you got to do is remove 3 things to now it's become an addition problem, and now we have 2 different signs. No, there's no need. So this idea that subtraction is only some extension of addition, that I don't need to worry about what this problem really means, I just change it into a different problem, especially for one that doesn't solve any differently than this. I mean, it's the exact same model. I mean, if you look at the pictures, the only thing that's different is that these were positives and these were negatives. So conceptually, procedurally, it's not that different. I mean, it's very much the same thing. So I'm not a fan of this because it clouds the issue about what's really happening with the mathematics here. Now let's move on to 3 minus 5. Now this is a little bit different because once I make my 3 negatives, well, I need to remove, I'm sorry, my 3 positives. What am I doing here? So I got 3 positives, and I want to remove 5 positives. And I don't have enough. So how do I get the 5 positives so that I can remove them? This is where we need to call back to what we tried to establish at the beginning, that 3 can be made a bunch of different ways. Because what I need are 2 more positives. But I can't just add 2 positives into this. I need to preserve value. So that means that I need to add in 2 negatives with them. I mean, these equal 0. So I haven't changed the value. This is still positive 3. It's a positive 5 with a negative 2, which makes that positive 3. But once I've established that I can do this, that I can add in these 0 pairs, and that 3 can be modeled flexibly, then this model is a piece of cake. Once I've got enough positives in here, I can go through and remove my positive 5, and then I see what's left is my negative 2. And that's it. Now, suppose a student, for whatever reason, adds in too many 0 pairs. And it's not uncommon to see students, when they add in these 0 pairs, that they might add in 5 0 pairs because they see that minus 5, and so they kind of panic. They freak out a little bit and they put in too many. Well, that's fine, because after I remove my positive 5, well, I've got some positive negatives left over. And remembering, hopefully, that these 0 pairs cancel, anything that was put in extra is just going to cancel out anyway. So a student could, if they were so inclined, put in 20 positives and 20 negatives, which is way too many. But in the end, as long as they remember that they shouldn't have both, and if they do have both, that means things can cancel, then the rest of this cancels out, and it's a piece of cake. We do the same thing over here with negative 3 minus negative 5. So I'm going to start with my 3 negatives. And again, this is going to be the same model from before, just with the signs inverted. So here's my negative 3. And so now I want to remove negative 5. I don't have enough negatives, so I put in 2 negatives, but to keep it balanced, I put in 2 positives. So I want to make sure this is still a negative 3. This is still a negative 3. We're good there. And now I need to be able to remove negative 5, and now I can. Boom. The negative 5 comes out, and I'm left with 2 positives. Again, I'm not doing anything with flipping signs around. I'm not changing this into plus positive. I'm leaving it as subtracting a negative. All I need to do is remove red chips. That's all I'm doing. There's no point in building this mystery of flipping signs around. There's just no point in it. Now, students might at some point see, hey, this is the same as, and that's better. I'm not going to say it's okay. That's better because at least they're connecting it to something. It becomes a shortcut to a method that has already some meaning to it. I don't mind that too much. Um, I'm not going to encourage it necessarily, and I'm not going to point it out. But this is built on a model that makes sense. All you really need to understand to make this work is that sometimes things add up to zero. And that is something that can make more sense to students than saying, well, flip these signs around and don't worry about why. That's no good for anybody. So that's how we subtract with positives and negatives. So now when we need to subtract positive and negatives with different signs, really the model doesn't change at all. I mean, once you've built a good model, if it has a lot of portability to it, which a good model usually does, once you put that in place, it's relatively straightforward applying it to different things. So once we look at these problems with different signs, you'll see that the mechanism, the model, hasn't really changed that much. So let's look at 5 minus negative 3. So we have a positive 5 and a negative 3. So I'm going to make my 5 positives. So we've got our first number. And now it's the same problem from before. I need to remove 3 negatives, but I don't have them. So I'm going to put in 3 negatives. But in order to keep it balanced, I have to put in 3 positives. And now I can remove my 3 negatives, which is what the problem needs me to do. And I look at what's left, and there's a positive 8. So I'm going to imagine that for some of you, you've always wondered how come 5 minus negative 3 can just become an 8, why it becomes that plus positive 3. And this is why. This is where that plus 3 has been coming from all this time. In order to remove this negative, you had to put in those positives to keep it balanced. And so there's your plus 3 right there. So yeah, here's your 3 minus negative 5. Same thing, 3 positives. I need to remove 5 negatives. But in order to put those 5 negatives in, I have to put in 5 positives to keep it balanced. Let's check to make sure this is still positive 3. Yeah, because all of this is a 0, so it adds no value. So this is my positive 3. All right. So now I need to remove my 5 negatives. So here's my 5 negatives. And they're gone. And so what's left here is positive 8 again. That's it. Once I know what subtraction is, that it's removing a set, once I know that I can model this flexibly using these 0 pairs, those two things combined make these problems fairly straightforward. Negative, we'll keep it like this, negative 5 minus positive 3 is going to be the same as this model on the left, but we're just going to flip the signs. We've got 1, 2, 3, 4, 5. I need to remove 3 positives. So I'm going to put in, again, this 0 pair here. I'm going to put in these zeros. And so now this lets me remove the 3 positives. And so what's left? 8 negatives. And lastly, same story. So we got 3 negatives. I need to remove 5 positives. In order to do that, I got to add in these 5 negatives also. So here's my 0 pair there. It's a slightly different color. I didn't mean to do that. Here we go. Remove my 5 positives. I count what's left. I got 8 negatives left. The main takeaway I hope that you take from this video and from this discussion around addition and subtraction with negatives is that if you've built models for all of these ideas beforehand, then you can explain these things in a way that makes sense. And students can make sense of the mathematics that they're doing rather than magically changing signs, rather than magically moving things around, rather than magically reallocating anything. There's no magic. I mean, it all should make sense. In order for you to make it make sense for your students, obviously it needs to make sense for you. So it's important that you know what these models are and how these models work. But once we've built these things for arithmetic, a lot of these models can apply into algebra as well. So they become very, very flexible ideas and very, very portable ideas about what we mean by addition, what we mean by subtraction. We'll use a lot of these same models for how we talk about multiplication and division. Um, you start to build a structure of how to make sense of mathematics rather than it just being this thing that you do and you don't know why you're doing it and you got to answer and you don't know where it came from and you don't know what it means. That's not doing mathematics. So what about the algorithm? Well, I mean, like I said, there's ways of building things around this. There's ways of doing different processes, but the algorithm, I don't have a problem with algorithms, but as I've been saying this whole time, algorithms need to be supported by something concrete. And so I don't have a problem with this necessarily doing these in step-by-step algorithmic ways. But they need to be supported by some sort of concept. There needs to be some sort of thinking about why you're doing what it is that you're doing. So, yeah. So for your checkpoint, I want you to think about sort of the expanded fact family problems for 4 and 7. So doing positive negative 4, positive negative 7, and then doing the possible addition problems, but also doing the possible subtraction problems in different order. Remember that addition is commutative. So for addition, 4 plus 7 and 7 plus 4, you don't necessarily need to do as separate problems. We've introduced commutativity now, so we're assuming that that we know they're the same thing, so it doesn't there's no benefit to doing both of them. But subtraction is not commutative. So if you're doing positive 4 and negative 7, so you're going to need to do 4 minus negative 7 and then negative 7 minus 4. What am I doing here? So yeah, so negative 7. My goodness, I'm making a mess of this whole thing. So let's do it like this, negative 7. There we go, that's better. So you'll need to do this one and then negative 4 and then negative 7 in both orders here as well. Negative 7, negative 4, because there are going to be different solutions because obviously subtraction is not commutative. So just make sure for positive negative 4, positive negative 7, you can solve all these problems. Not only find the answer, again, the answer is not really the point here, but that you can explain the answers for all of those. So if you have any questions about any of those problems or anything like that, make sure that you ask, bring it to office hours, bring it to class. All right, thanks.